Hi everyone. In this video we're going to come back to chiral molecules. Chiral molecules have a non-superimposable mirror image compound, and we call that non-superimposable mirror image compound an enantiomer. This compound here, if we mirrored it over, we would see that its mirror image is non-superimposable. Okay, I just want to give you a visual example of this. Let's say you took this compound here. Okay, we're going to put an ethyl on a solid wedge and OH on a solid wedge. We're going to mirror this over real quick. And when we mirror it over, remember, we're just changing kind of the directionality of the bonds. Here the ethyl is pointed kind of up and to the right, now it's up and to the left, but we're not changing the solid and dash wedges. When we mirror over, we keep those perspective wedges. What I'm now going to do is a little exercise here to show you how they are non-superimposable. What I'm going to do is flip this right compound over, and when I flip it over, instead of the ethyl being on the left side of the molecule, it's now on the right. But when I flip the molecule over, notice how the perspective wedges will change. Right? I am flipping this over like if you had your palm flat on a table and you flipped over your hand. Okay, that's kind of how you could visualize that. And now what I'm going to do is take this compound in red, which is identical to this one in blue. We just flipped it over. I'm going to show you how these are non-superimposable. Notice how the OH in the red compound is dash wedge, and that's not overlapping with the OH in the blue molecule because it's solid wedge. And similarly, the ethyl in the red molecule is dash wedge, and in the blue molecule it's solid wedge. These are non-superimposable, and they're not superimposing at each asymmetric center, right? Configurationally here, they are complete opposites. This would be R, this would be S, and the other asymmetric center would be S, and here it would be R, all right? So they're configurational opposites. R goes to S goes to R, and they are non-superimposable mirror images, and we just proved that. Remember, you can flip a molecule over, but when you do so, make sure to change all the perspective wedges. If you are simply just rotating a molecule in the plane, you don't have to change the perspective wedges. But if you flip a molecule over, again, that's like putting your palm flat on a table and then flipping over your hand, right? You have to change the perspective wedges. Now remember, if a molecule is chiral, it is said to be optically active. It will rotate plane polarized light. That's very important. So if I told you that a molecule is optically active, you know that it's chiral. And if a molecule is chiral, it has an enantiomer. And both of those compounds, your pairs of enantiomers here, they will each be chiral. They will be optically active compounds. If you have asymmetric centers in a molecule, it can be helpful to identify the relationship by doing R and S. And if those two compounds are configurational opposites, they will be enantiomers. But remember, at the end of the day, it's not that we're saying a chiral molecule has asymmetric centers. We're saying the definition of a chiral molecule is that its mirror image is non-superimposable. That's really important. Yes, in a lot of cases, chiral molecules have asymmetric centers, but not all molecules that have asymmetric centers are chiral. And we'll talk about that shortly, because those funky cases where we have asymmetric centers, but the molecule is achiral, are meso compounds.